So now that we've kind of built up a little bit of an intuition, let's start to think about how we can actually solve for this value of delta when we're given a particular value of epsilon. So in fact here maybe we can go back to the statement that we said here, which says that for any epsilon greater than 0 we can find a delta greater than 0 such that f of x minus L is less than epsilon whenever x minus a is less than delta. So the goal is to find a particular delta that guarantees that whenever x is within a distance of delta from a, then f of x is within a distance of epsilon from L. So if we're thinking about that here, well actually, yeah, so the first one here, let's look at the graph of f of x to find a delta where f of x minus 5 is within epsilon whenever x minus 3 is within delta. In this case, we'll look at 1 for epsilon. So that means we're going to go a distance of 1 away from 5 on the y-axis here. So we'll go up 1 and down 1. And so here's our little epsilon window that we're going to build around 5. And so we want to know, what does delta need to be so that the function values are always within a distance of 1 from 5. So we're looking for the x values that go with the y values in this particular window. So we can imagine here, well, okay, the points where f of x are equal to 4 would correspond to where x is 1 down here, and where f of x is equal to 6 would correspond to where x is 5 down here. So here I'm just kind of observing where the graph of f of x meets with those particular x values. So the question is, well, how far away from 3 are those values? And I can see here, well, 1 is a distance of 2 away from 3. 5 is a distance of 2 away from 3. So it looks like our delta that we're going to choose is 3. I'm sorry, it's 2. So here we can see that whenever absolute value of x minus 3 is less than 2, in other words, when x is within a distance of 2 from 3, f of x minus 5 is within a distance of 1. Or here, let's suppose I choose a different epsilon. In this case, epsilon equals 1/2. So now I'm going a distance of 1/2 above and below 5. And we can again try and figure out what x values those y values will correspond to here. So I'm building my little epsilon window around 5. You go up 5, or sorry, up 1/2 from 5 and then down 1/2 from 5. And let's see, what x values would those correspond to here and here. And of course I noticed that at x equals 2, that corresponds with 4.5 here. And then when x is 4, that corresponds with 5.5. So I can see that in this case, as long as I'm within a distance of 1 from the 3, then my function values will be within a distance of 1/2 from 5. So again here, if absolute value of x minus 3 is less than 1, then f of x minus 5 is less than 1/2, just from the graph. And we can probably also guess that if I were to take any value of epsilon here, I can always find a window around 3 to to get a distance for delta. And so that kind of leads, again, here to our precise definition of limit. And we sort of alluded to this definition earlier, but let's think about it again. So assuming f is well defined for all x in some open interval containing a except possibly at a, we say the limit of f of x as x approaches a is L, written in this notation, if for any epsilon greater than 0 there is a corresponding number delta greater than 0, such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is between 0 and delta. Okay, and again we've sort of built up to this definition a little bit, thinking about how we can interpret what this means and what this means. And because this definition is a lot more formal, this is the definition that you would use if, for instance, you wanted to make a proof about a limit, or if we had some general statement about a limit. This would be essentially the definition that we can rely on when we're doing some sort of formal proof about a limit. But for most computational examples, if I'm just computing the value of a limit, well, this definition doesn't really provide any added clarity. And in reality, the only time that this definition may be useful is in a context where you're trying to prove something, but not necessarily if you're just trying to evaluate a limit. We can always rely on just our intuitive understanding and our limit laws and various rules that we've developed over the previous sections. And to demonstrate this with a very simple example, let's consider the function f of x equals x cubed minus 6x squared plus 12x minus 5. And in this case, we're just going to quickly observe what the graph looks like as a way of demonstrating that that we can always find an epsilon such that f of x minus 3 is absolute value is less than epsilon whenever x minus 2 in absolute value is less than delta. And here's a picture, just a quick little picture of the graph. And we can see clearly in the graph that at x equals 2, the function value is 3. And if I build a little window around 3, then I can close in on the function values that correspond to any little window I want to build around 3. There's always going to be some little window around x, around 2 on the x-axis, that corresponds with those values. And no matter how tight I want to make that interval, I can just get it really tight. If I close in really close to 3, well, I can still find a corresponding window around x equals 2 that guarantees that those function values are close to 3. Okay, and again here I'm just using the picture to make my argument. We'll see in a moment how we can actually write out a proof more explicitly that will be a little bit more formal. What I'm doing here is certainly not formal, but it's hopefully maybe giving you a picture as to why this definition really does agree with the intuitive definition that we had before.